Hello and welcome to another session in physics. In this session we'll be looking at the topic photoelectricity, X-ray. But before that, let us review the previous lesson. Welcome back. Let's talk about photoelectric effects. Remember we said when light falls on a metal surface that some electrons are emitted. These electrons that are emitted are what we call thermionic emission. But for the sake of this topic, if you're asked to define photoelectricity, you say that photoelectricity is a phenomena that occurs when electromagnetic radiation is focused on a metal surface and electrons are liberated. Also, like I said earlier, when light falls on a metal surface, electrons are emitted. This process is called photoelectric effect emission, and the emitted electrons are known as photoelectrons. So photoelectric effect emission and thermionic emission are basically the same principles. The maximum kinetic energy of the photoelectrons are independent of the intensity of the incident light, but depend on the frequency or wavelength of the incident light. In WAEC, you may see a question of this nature. One of these factors affects the kinetic energy of photoelectrons. Option A, intensity. Option B, frequency. Option C, wavelength. The truth is that the answer is wavelength and frequency. Frequency and wavelength. These are the two things that affect the maximum kinetic energy of electrons. Intensity does not affect the kinetic energy of electrons, but the kinetic energy of electrons are dependent on the frequency of the wavelength of the incident light. It's also important to note that increasing the intensity of light increases the number of photoelectrons, but it does not increase the energy or velocity of electrons. The absorbed energy of these electrons is used to overcome the potential barrier of the photoelectrons, the barrier that the photoelectrons would experience. Now let's look at the practical applications of photoelectric emissions. Photoelectric emissions is used in the following: in the construction of burglary alarm, in the construction of television camera. It is also used in automatic devices for switching lights at dusk. Example, street lights. As you can see in the diagram here, we use photoelectric emissions to automatically switch on these devices at dusk. Our street lights as well. And then we have sound tracks, sound production of film tracks. Photoelectric emissions are used as well. We also have industrial controls and counting operations. All these work on the principle of photoelectric emissions. Now, Albert Einstein propagated a theory and subsequently produced an equation known as Einstein's photoelectric equation. Einstein's photoelectric equation is given by energy of the photon, which is E, equal to the work function, which is this, and the kinetic energy of the photon. Kinetic energy, which is given by this as well. Also, the work or the energy possessed by the photon is given by Planck's constant times the threshold frequency. Of course, we've mentioned that altogether is the maximum kinetic energy that can be given to a photoelectron. W is the work function. Of course, W here, O is the work function. And then this is our threshold frequency. And this is the maximum energy of the liberated photoelectrons. So Planck's constant times the frequency gives us the maximum energy of the liberated photoelectrons. Now let's talk extensively about threshold frequency and work function. Threshold frequency, denoted by F and is subscripted O, simply refers to the lowest frequency that can cause photoemission of electrons from a metallic surface. Below the threshold frequency, it's important to note that electron emission cannot occur. Work function, on the other hand, is given by the Planck's constant times the threshold frequency. and it is referred to as the minimum energy that is required to liberate electrons from a metallic surface. Now let's look at this question we have here. We're asked to compute the frequency of the photon whose energy is required to eject a surface electron with a kinetic energy of 3.5 times 10 raised to power minus 16 electron volts if the work function of the metal is 3.0 times 10 raised to power minus 16 electron volts. Now the solution to this question is very simple. Already we have Planck's constant and we have the value of 1 electron volt. So we're going to use this equation, E equal to HF minus W, and then we have E plus W equal to HF. So we can also have E plus W equal to F, and this E plus W is over H. So everything together, our calculations are going to look like this: 3.5 plus 3.0, 3.5 plus 3.0 times 10 raised to power minus 16 times 1.6 times 10 raised to power minus 19 all over Planck's constant 6.6 times 10 raised to power minus 34, and it's going to give us 6.5 times 1.6 times 10 raised to power minus 16 minus 19 plus 34 all divided by 6.6. We've already taken care of the power to 34, so the indices minus 34 went up and became plus 34, so everything here is going to become 1.58 times 10 raised to power minus 1 hertz. This is the frequency of this particular photoelectron. So that's what they asked us to calculate, the frequency, and this is the answer to the question, hertz. Alright, let's look at threshold wavelength as well. Threshold wavelength simply refers to the longest wavelength that will produce photoelectrons when the surface is illuminated or irradiated or faced with electromagnetic radiation. And this threshold wavelength is given through this equation: work or energy equal to Planck's constant times threshold frequency, and we have W equal to Planck's constant times speed of light over lambda, which is the wavelength. So we can make wavelength subject of the formula threshold wavelength, where we now have wavelength equal to Planck's constant times speed of light over W. This is the formula for threshold wavelength. Now let's talk about X-ray. X-ray was discovered in 1895 by Wilhelm Röntgen. X-rays are produced when thermally generated electrons from a hot filament are accelerated through a high potential difference, and they are focused on to a tungsten target where the electrons are suddenly stopped. Because of the sudden stoppage of these electrons, then rays are emitted. These rays emitted are called X-rays. Now the mode of operation of the X-ray is that in an X-ray tube we have a high potential difference applied between the hot cathode and the anode. Electrons are then emitted from the cathode and are made to accelerate at an extremely high speed. They are abruptly decelerated, or they start to slow down until they come to rest when they strike the anode, which causes the emission of high energy radiation of short wavelengths, that is X-rays. The anode then becomes very hot in the process, and it requires cooling genes on the outside of the tube. This is how X-rays are produced in an X-ray tube. Talking of energy conversion during X-ray production, electrical energy is converted to thermal energy. Then thermal energy or heat energy is converted into mechanical energy. This mechanical energy precisely is kinetic energy, which helps to accelerate or get the electron moving. The mechanical energy is then converted into electromagnetic energy of the X-ray. This is exactly what an X-ray tube looks like. Now we have different kinds of X-rays, and the types of X-rays are of basically two. We have hard X-ray and soft X-ray. Now when it comes to hard X-rays, they have high penetrating power or ability, and they have shorter wavelength. But for soft X-rays, they have low penetrating power and they have a longer wavelength. When we talk about hardness of an X-ray, we are simply referring to a measure of the strength or penetrating ability of that X-ray. And when we talk about the intensity of an X-ray, we are referring to the energy that is radiated per unit time, per unit area by the X-ray. And of course, this depends to a large extent on the current of the filament. Now, talking about properties of X-rays, X-rays are electromagnetic waves and they have high frequency, but they also have short wavelength of about 2 × 10⁻⁻10 meters. X-rays also have high penetrating power. X-rays are known to travel in a straight line. They are also not diffracted by either electric or magnetic fields. Also, they are not diffracted by crystals. They also ionize gases and they cause zinc sulfide to fluoresce. When we say fluoresce, we mean glow. Now let's look at the applications of X-ray. One of the applications of X-ray is that it is used to examine the body to locate broken bones. It is used to detect metals and contraband in a baggage. They are also used to detect cracks in welded joints of pipes and other materials. And they are used to investigate the crystal structure of a substance. They are also used in the treatment of tumors and malignant growths such as cancerous cells. And in agriculture, they are used to get rid of bacteria and kill germs. Now, everything that has an advantage also has its disadvantage. So at this point, let's talk about the hazards of X-rays and precautions we can take to limit them. One of the hazards of X-rays is that due to their power and strength, they can cause genetic mutation. They can alter the DNA of someone and cause serious problems in the body of someone. They can also destroy body cells. They can cause blood issues when they damage body tissues and cause diseases such as leukemia. They can also cause skin burns and cancer. So they are very, very dangerous. One of the precautions and the best advice that can be given to anyone who comes in close contact with X-rays is that anybody who works with X-rays should always put on lead coat and they should go for checkup, medical checkup regularly. And that's it for today's lesson. Thank you very much for joining us. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.